So with that in mind, let's talk first about how we might quantify these sort of two basic concepts like availability and responsiveness. The gold standard for availability is the US public phone system, which set this ambitious goal that they were going to be available 99.999% of the time. Because that's a hairball to say, we just say 5 nines. And there's a joke in Release It, which is a really good book about deployment and operations, where the author claims that most internet services are more like 2 8s rather than 5 nines. They're up 88% of the time, maybe. But if you do the math, 5 nines comes out to about 5 minutes a year. So that means that the goal is during any given year, there's no more than a 5 minutes worth during that year where somebody picks up the phone, is unable to get a dial tone and place a call. And since each 9 represents an order of magnitude increase, if you did 4 nines instead of 5 nines, that's 10 times as much downtime, so it's 50 minutes a year and so forth. Good internet services, good SaaS, 3 to 4 nines is not a bad target to aim at. And the well-run ones tend to be in the 3 or 4 nines range. The response time is how long after I interact with the site do I get a response. And it used to be when people were connecting using slow modems that the response time was often dominated by the bandwidth, right? If you were downloading things like images and other rich content over a slow connection, the time it takes to get to the first byte was small compared to the time it takes to download all of the bytes. Now, given that most people have broadband in the home and at work, what we find is that for SaaS applications like the ones we're building, response time tends to be dominated by the initial, how long does it take to get the first byte back? Because once you've got the first byte back, the bandwidth is so large that you can get the additional bytes in a very short amount of time. So now it's really dominated by latency as opposed to bandwidth. And as we'll see, that's a really important distinction for SaaS applications, because you don't have much control over the bandwidth from you to the user, but you do have control in many cases over how to make the latency better. In case you don't think response time is important, there was a famous experiment that was conducted across 3 companies not known for cooperating with each other, and they found that by artificially introducing delays in the response time, Amazon was able to see a 1% drop in sales just by introducing 100 milliseconds, so basically a 1/10 of a second difference in response time injected into a random subset of users. Yahoo and Google saw drops in the amount of traffic or the number of searches they were doing. So if you're turning over a lot of volume, response time really matters. And interestingly, there were 2 classic studies from the human-computer interaction literature that were like 40 years apart, but 32 years apart, and had very similar results in terms of what the user thresholds were. If something happens within less than 100 milliseconds of you taking an action, your perception is it's instantaneous. So in some sense, that means there isn't a huge benefit to going lower than strictly 100 milliseconds. And if something takes longer than about 7 seconds, your brain gets distracted and starts to float away to other tasks. So that's the abandonment time. And remarkably, a study, so in 1968, there was no web. The study was based on interactive computer programs that were not web-like. But the 2000 study was done with a website that was basically built to simulate an e-commerce site and where they could inject these different delays. And it was quite interesting that they reproduced the same results. Jeff Dean, best known as one of Google's senior architects and now a Google Fellow, which is like the highest technical title I think you can have there, is well known for saying speed is a feature. So speed is not an optional component of your application. And Google has a great, great website that has articles on every conceivable aspect of what you can do to make your SaaS applications faster, which I recommend you check out. This is the view of performance most people have when they start out, and it's totally wrong. So let's get it out of the way early. We have this nice bell curve of performance, and the performance is kind of normally distributed. So that means that whatever the average performance is, that's a pretty good representation of what users are getting. And some users are going to be 1 or maybe even 2 standard deviations out to one side or the other. As we all know, for a standard normal distribution, once you get to 2 standard deviations out, you've got 95% of the users. So even in that worst case scenario, you could argue that 95% of the users are getting a response time that's 2 standard deviations out from the mean. And by the time you get 3 standard deviations out, you've pretty much got everybody. So nobody is really getting worse response time than t plus 3 standard deviations, right? Whatever this middle point is. Unfortunately, as it turns out, this is not what real-world performance looks like. It looks more like this. And this is actually a real entry that I found this year from an engineer at New Relic, which we'll talk more about. They're a really nice site for doing monitoring of your PaaS-based apps. This is a histogram where the y-axis is the number of requests, and the x-axis how long in milliseconds it took the request to complete. So the green line is the average, the arithmetic mean, which is around 2,600 milliseconds maybe. But what's this line out here, the dotted red line? This is the 95% the 95 percentile, right? So 95% of users are getting performance that's somewhere in this wide band, right? This is way more than 2 sigma out from the average, as you can see. Half of the users are getting performance that's worse than this, right? So this, the shaded red area here covers the 25th percentile up to the 75th percentile. So what we care about in these sites is not really what is the average user perceiving, right? What we care about is, are most users getting good service? And under the mistaken assumption that performance is normally distributed, you would use a graph like this to figure it out. But when you realize this is reality, it means this is the number you have to worry about out here, right? 95% of the users are getting an experience that's no worse than this, but this is pretty bad. Now we can talk more clearly about service level objectives and service level agreements. The SLO is, if you talk about the time to satisfy a user request, what's the latency the user perceives on a particular kind of request, we talk about what percentage of users are getting performance within a certain threshold, which means we have to specify a time window. Because if we say 99% of users get a response in less than 1 second, it still doesn't tell us, well, over what window are you measuring? Because if you're measuring over a year, and you're saying 99% of the users over a year are seeing less than 1 second response time, you can get away with a lot as compared to saying in any 5-minute window you've got to do better than 99%, right? So the time window actually matters quite a bit. And if you hear the term service level agreement or SLA, that's just an SLO with lawyers, right? So the SLO is the technical expression of what you're supposed to achieve. The SLA is a contract that says what bad things happen to you if you fail to achieve it. A simplified way of computing the SLO, which it's not uncontroversial, but it does give you sort of a good middle ground. It's called Apdex for application index. And basically, instead of having to talk about thresholds on everything, here's a simpler version. We'll pick a threshold latency for a typical request, call it T, and we'll say that a user is satisfied if a request takes less than that amount of time. They tolerate it if it takes up to 4 times that long, and otherwise they're unsatisfied. And basically, we're just computing a weighted average that over any given time period, we look at how many satisfactory requests, in other words, within time T, and you get sort of half credit for the requests that were tolerated and no credit for the ones that were greater than 4T. You divide that by the total number of requests, and that's your Apdex score. So a score of 1.0 basically means every request was within the T threshold. Scores of 0.85 to 0.93 are considered pretty good, so that's kind of a good rule of thumb to aim at. And a reason that this is not uncontroversial is that if you're careful, or if you're not careful about how you use it, you can hide systematic outliers. So the classic example is, let's say you have an e-commerce site, and every action is really fast, except the checkout action takes 10 times as long as all the other actions. And if the checkout action only occurs once out of, if it takes 15 clicks to get to the point where you're ready to pay, and you're losing people on the payment page because payment takes so long to process, Apdex won't tell you that, right? Because Apdex will show, look, you only had you're only getting penalized for 1 transaction out of every 15. That's not enough to make your Apdex score go below 90%. So from Apdex's point of view, you'd still be doing just fine, but you're losing all of your users at the point where it's most painful to lose them. One way that you can guard against this is a lot of monitoring systems will let you set different Apdex thresholds for different transactions. So page views and browses have one threshold, and long-running operations like a purchase might have a separate one. Here's the same histogram from before, but this time the coloring has been modified to show the Apdex regions. So the yellow or tan, whatever color you'd call this, these are the requests that were under the Apdex threshold, which was set at 1,500 milliseconds. And the red is the ones that were greater than that, but less than 4 times that. So here's 6,000 milliseconds out here. And the black are requests that were beyond that. And you can see from the indication that there's 3.6% of the requests that are off the chart here. And we can't tell how far off the chart they were. So if you actually did the math for the sort of raw data underlying this histogram, you would get an Apdex score of about 0.7, not abysmal. But if you take that exact same distribution and just shift your Apdex index, your threshold, from 1,500 milliseconds down to 1,000 milliseconds, right? So now here's the coloring. So same distribution. So all of a sudden, the performance score for Apdex has gone down to 0.49, which is pretty bad. The lesson I would not want you to take away from this is if you have a poor Apdex score, just keep shifting the threshold until the calculation makes it come out at greater than 0.8, right? So a rule of thumb is if you do some benchmarking on your application, you can get a typical sense of where you would expect this peak to be and set your Apdex score somewhere in there, because then when your Apdex score starts falling below threshold, it's actually an alarm that some transaction or some request is taking much longer than you probably expected. So it helps you sort of pinpoint where the slow request might be. And what do you do if your site is slow? Well, honestly, for a small site, and that includes a lot of the projects you'd be building for this class, it's perfectly reasonable to just over-provision by a little bit. Put in a little more capacity than you need. That used to mean buying more computers, but today it actually means using one of the horizontal scaling systems that in some cases are built right into PaaS. RightScale is an example of a system that does this on top of AWS deployed applications. So over-provisioning is not a terrible solution because you're only paying for it when needed. You're paying as you go. If you have a large site, you have to worry. Because if you have 1,000 computers and you can't just over-provision and say, I'll buy 100 extra computers and keep them idle for when nothing happens, right? That's a poor use of capital and operating expenses. So the thing that's going to save us, and the reason that these two are tied together, is that the same problems that would push us out of the regime where we can run successfully on PaaS, those are the exact same problems that are going to require attention if we want to scale out our application once we bring all that stuff in-house. So understanding how those problems arise and how you solve them has two benefits. The first one is it'll keep you longer in that PaaS tier where many more of those things are taken care of for you. And second is when you do get to the point, if you ever get there, where you have to do all this stuff yourself, you'll understand what the underlying causes are and you'll have some ideas about how to engineer the solutions. So here's a question to see if that sank in. Rotten Potatoes has a target uptime of 3 nines, but yesterday it had a 1-hour outage. Which of these statements is true? That because of the outage, it's got no hope of meeting its uptime goal for the year, that it can still meet its uptime goal if there's no further outages this year, that if no users actually tried to get to the site during the outage, there was no uptime problem. It's like a tree falling in the forest. If nobody hears it, didn't really fall. Or there isn't enough information to determine.